Alright guys, welcome to part 2 of the 8.4 video. So in part 1, we discussed a few different things. The main idea here is that the strength of an acid depends on the degree of ionization. Same with a base. The strength of an acid or base depends on the degree of ionization. So strong acids and bases ionize fully or close to fully in solution, whereas weak acids and bases ionize only partially. So one thing that's emphasized here is how these different properties, conductivity, pH, and rate of reaction, will differ whether your acid or base is strong or weak. Okay, we're going to start with electrical conductivity. So how well a solution will conduct electricity. In a strong base, because the strong acid or base, because the degree of ionization is very high, you're also going to have high electrical conductivity. Okay, you're going to have a relatively high concentration of ions in that solution. You're going to conduct electricity pretty effectively. With a weak acid or base, you're going to have lower electrical conductivity. Okay, because the concentration of ions is going to be lower. Okay, and you need ions in solution to conduct electricity. Okay, so that one pretty straightforward. pH is the next property we're going to talk about. And pH was mentioned in the 8.3 video. So if you haven't already gone through those, you might want to revisit the concepts behind pH, okay, and how the pH scale is determined. So you'll remember that the pH scale goes from, well, the scale that we use in most cases goes from 0 to 14, where closer to 0 represents a stronger or a more acidic solution, and then closer to 14 represents a more basic solution. Okay, so this one, pH, is actually going to differ a little bit depending on if you have an acid or a base. Okay, if you have a strong acid, your pH is going to be close to 0. Okay, if you have a really strong acid, you might even have a negative pH. Okay, so like a very high concentration of a strong acid. Okay, although when we talk about these properties, usually we're talking about a 1 mole per liter solution. Okay, so the lowest possible pH of a 1 molar solution is 0. Okay, so if you have something like a 1 molar solution of hydrochloric acid, it's going to have a pH of 0. Okay, and then a 0.1 mole per liter solution of hydrochloric acid would have a pH of 1. For a base, if you have a 1 molar solution of a strong base like sodium hydroxide, then you're going to have a pH of 14. Okay, so strong acids and bases are going to be around the extremes of the pH scale. Okay, your acids are going to be close to a pH of 0, your bases close to a pH of 14 when they're strong. When they're weak, you're just going to close in closer to that neutral pH. Okay, so 7 is the middle of that 0 to 14 pH scale, and it represents a neutral pH, where acidic and basic properties are balanced in the solution. If you have a weak acid or a weak base, you're just going to have a pH closer to 7. If it's an acid, it's going to have a pH less than 7, so maybe something like 4 or 5. And if it's a base, it's going to have a pH over 7, so maybe something like 8 or 9. But a weak acid or base will have a pH closer to that neutral middle range. Okay, and then the last property we're going to talk about, the chemical property rate of reaction. A strong acid or base is going to have a fast rate of reaction. Okay, a weak acid or base, slower. Okay, and we have encountered when we talked about rates of reaction in topic 6, we talked about how we might measure a change in a certain property to get an idea of the rate of reaction. So if you have a strong acid, you're going to get a very fast reaction. And if you have a weak acid, you're going to have a slower reaction. A good example of this, if you recall the hydrochloric acid and magnesium metal lab we did, you saw how the rate of reaction varied with different concentrations of acid. Okay, but know that we were always using a strong acid in that case. If I had selected a weaker acid to do the reaction, something like, say, acetic acid, which is a pretty abundant chemical storeroom classic, you would have noticed that the rate would be even slower. Okay, so the rate of reaction could depend on the concentration of the acid, but it will also depend on whether it's strong or weak. The last thing I'm going to go through here is just some examples of different reactions with different types of compounds and acids. Okay, so when we talk about rates of reaction right here, often we're referring to reactions between common types of compounds or elements, in the case of the first example, and acids. Okay, so I'm just going to go through here. It's not a bad idea to sort of review predicting products and then balancing chemical reactions. It's a skill that's pretty important across chemistry, and then we'll be done. Okay, and I had to make myself a little cheat sheet here because being put on the spot, even though I'm recording a video by myself in my house, I still am a bit nervous about making a mistake. Okay, so our first reaction here, we've got a strong acid, nitric acid, with calcium metal. Okay, so this is an active metal. Active metals are like metals in group 1 or 2. Okay, so like the alkaline metals or the alkaline earth metals. So calcium in group 2 is an active metal. It would react with an acid to produce hydrogen gas, so it would definitely bubble. And it's also going to make a salt with the conjugate base of that acid. So we would make calcium nitrate in this case. Okay, and then that reaction isn't balanced. So I'm going to go through and balance it. You notice that I'm making hydrogen gas, which means that I'm going to need 2 of these acids. And then that also balances out the nitrates here. Okay, next reaction. So I've got an acid with a metal oxide. So in general, I'm going to make a salt and water when I react an acid with a metal oxide. So water is one of my products, liquid. And then the salt here is going to be made up of whatever the conjugate base of the acid is and the metal. Okay, so in this case, that's going to be iron. And I can keep the oxidation state the same. So this is iron 3, so it's going to be iron 3 chloride. Okay, and then to balance that, I'm going to need 2 acids. Wait, no, 6 acids, because I'm going to make 3 waters, because there's those 3 oxygens there. Okay, and then I'm going to need a 2 right there. All right, next reaction. This is actually, the way it's described, acid with metal hydroxide, maybe makes it seem a bit more complicated, but this is actually a very straightforward acid-base neutralization reaction like you would have seen in grade 10 science. Okay, so I'm going to make a salt. In this case, it's going to be potassium sulfate, K2SO4, and water. Okay, and then I just have to balance that out. So I know that I'm going to need 2 of my potassiums, and then that's going to make 2 waters. Okay. Then the last 2 examples deal with carbonates. The first one is a hydrogen or bicarbonate salt, and then the next one is going to be just a normal carbonate. So I've got phosphoric acid, which is a triprotic acid, which just makes balancing this a little bit trickier. And then I've got sodium bicarbonate, which is also known as baking soda. So when an acid reacts with metal hydrogen carbonate, like this one right here, I'm going to make a salt with the metal and the conjugate base of the acid. So that's going to be Na3PO4, sodium phosphate. And then I'm going to make, it can be tempting to just be like, oh, and then it's a double displacement reaction, so I make H2CO3, carbonic acid. Actually, though, carbonic acid isn't a very stable molecule, and you get, I mean, the chemistry here is a little bit more complicated than I'm going to make it look by this reaction, but usually the carbonic acid will actually decompose into water and carbon dioxide, which is why I get that fizzing when baking soda reacts with an acid. Okay, so this is a liquid and this is a gas. Oh, I forgot my state symbol up here too. Okay, then to balance that, let's see what I need here. I need 3 of these, so I can make 3 waters and 3 carbon dioxides. Okay, and then my last reaction here, I've got an acid. This is a bit of a different acid. It's an organic acid. Acetic acid or ethanoic acid, which we're going to be learning about when we start topic 10 next week. And then just a metal carbonate, no hydrogen included here, calcium carbonate. So here, once again, I'm going to make a salt with the metal and the conjugate base of this acid. So this acid, the formula is written like this because the acidic hydrogen is listed on the end here. So the conjugate base is going to be just this part. Okay, so I'm going to make calcium acetate, COO. And then because calcium has a valence of 2, I need 2 of those. That's going to be a soluble salt. And then I'm going to make water and carbon dioxide. Okay, so when you have a carbonate present, you're going to make water and carbon dioxide. And then to balance that out, you're going to need 2 of your acetic acids. Okay, and then everything else works out pretty nicely. Okay, so in part 2, we covered just some properties that you can expect if you're dealing with a strong acid or base versus a weak acid or base. And then we looked at some examples of acids reacting with some common types of compounds, or in the first case, elements. Okay, thanks so much. These are your practice questions. They're in the textbook. If you don't have your own copy of the textbook available, just let me know. I can send you a screenshot of just those questions. And that is it. I'll see you guys in the Google Meet maybe.